Hi, I'm Serge Egelman, and I'm the research director of the Usable Security and Privacy Group at the International Computer Science Institute, which is a research institute affiliated with UC Berkeley. I'm also the co-founder and CTO of AppCensus, which is the commercialization of some of this research. Today, I was going to talk about some of the tools that my research group has been building for studying mobile app privacy behaviors and how we've been using these tools to look at compliance at scale. And by compliance, I mean whether apps are complying with their privacy policies, as well as laws such as the GDPR in Europe. And in the US, we've been starting to look at COPPA, which is the Children's Online Privacy Protection Act, as well as CCPA. We found that many of the really questionable behaviors that we find from mobile apps are due to third-party SDKs. In many cases, it's likely that developers don't even know that their apps are engaging in these behaviors. And so the bottom line from this talk is that while code reuse has created many benefits in terms of rapidly being able to add functionality into apps, increasingly we're in a situation where it's causing severe problems for compliance. And I hope that from this talk you'll be able to be a little bit more cognizant of these issues so that you can avoid them in your own work. So in terms of my research, my group has been spending, I guess, probably about the past 10 years now studying Android and mobile app privacy behaviors. We've specifically focused on Android just because it's open source. We have the source code so we can add instrumentation into it so that we can monitor mobile apps when they're run on our devices. That's why we don't do this on iOS, simply because we don't have the source code, and so we don't have the same level of instrumentation. It was about 4 years ago that I was chatting with a colleague who's been spearheading a related project at ICSI, where they've been building traffic monitoring tools. And so we decided to combine our tools to build an end-to-end pipeline so that we can run apps on mobile devices to see what types of sensitive user data they access, and then to whom they send it. So basically, we have a whole process now where we download lots of Android apps. We run those apps on our instrumented phones in our test bed so that we can observe what data they access and to whom they send it. And then we look at what APIs were accessed, which will give us clues as to what data might be used for, such as ads or analytics, as well as what types of third-party SDKs were present and whether those were responsible for many of the data exfiltration behaviors that we observe. And so at this point, basically our office looks like a click farm. We have a whole bunch of phones that are running our custom version of Android, and we have a series of scripts that push apps to them for testing. The apps are run automatically using what's called the exerciser monkey, which is a tool that comes with the Android developer tools to basically fuzz the UI. It generates random UI events such as taps and swipes and so forth. And so apps are running automatically on these phones, and then in the network traffic, we look for various known types of personal information, such as the email address associated with the device, the phone number, location information, and so on. We also look for a whole slew of different persistent identifiers. And for all of this data, we look for both the data in the clear as well as different permutations of it, such as various types of hashes or encodings, such as base64, for instance. And so, as I said, there's a whole pipeline. We have an app repository. We push the apps that we download to the test bed, and then we simulate the user interactions using the monkey, as well as we sometimes run apps with real human input as well, which I'll get into. All this goes into a results database, basically the logs that get pulled off the phone and augmented with the traffic flows that we observed, and then all the data is accessible by API, and we also have a website where you can search for reports on individual apps. So here's just a view of how we test an app, just so that you have a better understanding of what we're actually doing behind the scenes. So we have a dashboard. We can type the name of an app, the package name, or even just a link from the Play Store. We could specify which region we want to test the app in, such as the US, or Europe, or we have a bunch of different countries where we have infrastructure. And then we could specify what type of device we want to test it on, and whether it's an actual human testing versus the monkey, which I described previously. And so if we specify the human, we have a remote desktop solution so that you can actually interact with the app in the browser here. So, using the dashboard, you can, fully interact with the app if you want real human input. And that's actually running on a phone somewhere else in the world. But at the end of the day, the whole point of this is to generate data. So after interacting with the app, it halts execution, and our tools pull all the logs off and then parse them to see what actually happened. So the things that we're generally interested in are what are the type of what are the types of personal information that are collected, and where do they go? So more often than not, when we're talking about personal information, it's usually just persistent identifiers, and the one that we most often see is the Android advertising ID, which is what's shown here. Here we see the advertising ID is being collected by double click, but we see connections to other servers elsewhere as well, though no detected personal information during this particular test. We also, look at stuff like what SDKs were bundled within the app, what permissions were used, and so forth. And so, it should be obvious how we can, how we're using these tools to look at compliance. So this actually started, though, stepping back, once we decided to build this pipeline to test apps, and we just started, crawling the Play Store to download lots of free apps so that we can run through a test bed. And then early on, I started making queries to see what are the interesting behaviors that we can examine with all this data that we're collecting. And one was I wanted to see who was the most prolific sharer of location data. And the results came back, from that query that CVS was sharing location data with 40 different third parties. And at the time, we had just built this, we were still testing it internally. My assumption was, oh, this must be a mistake. There's got to be a bug in our code. But there was no bug, and in fact, we just discovered a big privacy bug on their app. So the CVS app is actually a series of web views. So a web view is just a widget that's basically a light web browser that allows you to load web content in a mobile app. And so basically the whole CVS app is a series of web pages that get loaded in web views, and that's it. But what was happening here is that the user agent string, which describes the version of the browser, and in the web view you can set that to mimic different browsers. Whoever wrote the app was adding the GPS coordinates into the user agent string, which meant that any third-party content that was loaded from that web page would also receive headers that included this user agent string, including the GPS coordinates, which is how it was being sent to 40 different third parties. So this immediately showed how this was useful for detecting these types of issues. And in this case, the second lesson learned, though the tangential from this talk, is on the importance of having technical contact information. So after finding this bug in the app, I tried to contact someone at CVS to report this to, and after spending about an hour trying to find someone who would reasonably be the person responsible, I gave up and finally just emailed customer care, and they said, no, I'm mistaken. They don't share my location information with any third parties, clearly not understanding the issue. And so at that point, we actually set up a blog and blogged about it, which got some press coverage, and CVS fixed it within a week after that. But again, one of the takeaways is have contact information accessible so that when issues like this arise, it doesn't, to get them resolved, doesn't rely on going to the media. But stepping back to the main point, from a lot of this early work, we began to realize that a lot of these privacy issues that we're seeing are coming from third-party services and not necessarily core app functionality. So here's an example of one. So this was a children's app that we looked at early on, and we found in yellow here it was sending data to this host, talkingdata.net, which is a analytics provider in China. And you can see it was sent over port 80, so it was unencrypted. And in blue here, it lists all of the identifiers associated with the device, as well as in green, it has information about the Wi-Fi hotspot that we are connected to, which can be used to infer location information. This, incidentally, is likely illegal under the U.S. Children's Online Privacy Protection Act. So this is actually the only comprehensive privacy law in the U.S. currently. Most other laws that relate to privacy are sector by sector, whereas under COPPA, any data collected from children under 13, regardless of what sector, is subject to various restrictions, such as prohibitions on behavioral advertising. Certain types of personal information, such as location data, require verifiable parental consent, and any personal data needs reasonable security measures, such as the use of TLS. And so, you can see many of these appear to be violated in that example. And so we decided to dig deeper, and we started building up a corpus of children's apps, and we found that there was evidence that the majority of the apps that are specifically designed for children appear to be violating federal law. And most of it comes from collection of various types of non-resettable identifiers that allow for profiling, and having those identifiers being sent to services that are specifically for behavioral advertising and profiling, as well as non-use of TLS. And as I said, by and large, this comes from third-party SDKs. So we published this, and it got a lot of attention. There was a state AG actually filed suit against an app developer, as well as several of the third parties that were bundled in the app. The New York Times sent a photographer to my office who said too many plants, not enough blinky lights. So I got to go to the machine room for the first time in my life for a photo shoot. That was fun. But anyway, the real impact was Google actually changed their policy. So Google, in response to this, started requiring that any third-party ad networks only come from this pre-approved list. This is probably expanded since. But the point is, all of the certified ad networks that are allowed in kids' apps are certified because they allow developers to disable the behavioral advertising. The problem is compliance is self-certified, so it relies on developers to say that they're only using ad networks that are on the list. But more importantly, there isn't really any follow-up as to whether if the SDKs that are on this list are even correctly configured. So while they allow the developers to disable behavioral advertising, there's an open question as to whether the developers are actually doing so, and whether the developers even know to do so. Because in many cases, it's unlikely that it's malice, but most likely misconfigurations, because developers have a lot to think about. So here's an example of one. So here's Ad Colony's documentation. It explains that if the app is going to be, if it's a child-directed app, you need to select this option in the Ad Colony dashboard, and as a result, that'll give it COPPA compliant treatment by disabling behavioral advertising. Similarly, here's another dashboard thing from Chartboost. It took me a non-insignificant amount of time to actually find documentation for both as to how you actually enable these options. Here's another one. Here's Kochava. This is a snippet of code that developers are required to add to their apps to tell the Kochava SDK to disable tracking. And so the problem with all of this is that it relies on developers, knowing to find this documentation, understanding how to do it, and then correctly doing it. And none of that is actually mandated by Google. It's just that developers must certify that they're only using these particular ad networks. And so we retested this about a year and a half later, and we found that, certainly as expected, there's plenty of use of not just the unapproved ad networks in kids' apps, but many that are approved don't appear to be correctly using the tracking opt-outs from our testing. That said, it's been over a year and other behaviors have improved, such as, the amount of location data that's being collected has, been reduced to a third of what we measured before, and same thing with, TLS non-usage. Now, only about 16% of apps appear to be sending data insecurely, which, isn't great, but it's still better than 40. And so, one of the problems with this, though, why it's hard for, say, Google to verify that SDKs are being used correctly, the same reason why it's hard for developers to verify that they're using the SDKs correctly. Each SDK has its own API with its own documentation that developers must just figure out. And so, one of the big questions is, do developers know to actually look for the documentation when you're going to use a third-party SDK to solve some, task in your app? Do you know to look for relevant privacy options? When configuring that SDK, do those in your organization who are responsible for compliance understand how, configurations of the SDK have a profound impact on the app's privacy behaviors and whether or not the app is complying with its privacy obligations? And so, while a lot of this is due to bad documentation, which makes it hard for developers to figure out what they're supposed to do and requires them to put concerted effort into. Um, at the same time, we found a lot of SDKs that appear to be just outright malicious, which means that there are likely many app developers that are bundling SDKs and not knowing, legitimately, despite their best efforts, that the SDK is misbehaving. So we published a paper on this last year where we looked at apps that have been circumventing the permission system. Basically, what we did was using our framework, we started auto-detecting side channels and covert channels that apps are using. And what I mean by a side channel is basically a way of bypassing a security mechanism. So the app, tries to access, say, location data, but it's protected by the permission system. If that location data is available elsewhere on the device, in a place that isn't protected by the permission system, that's known as a side channel because the app could then access the data in that place, thereby, circumventing the permission system. Covert channels is a similar thing, but basically this relies on two apps colluding, such that one app that might not have access is still able to get the data because it's talking with an app that does have access. And so using our infrastructure, we can, automatically test for this. We can look at, what are all the apps that are sending personal information out, and then we can look at what are the apps that are allowed to send, that are allowed to access the personal information. And, if we subtract those two sets, anything that's left means that that's, an app that's sending out personal information that it didn't have the right to access, and therefore it's circumventing the permission system somehow. So here's a look at how that might work. So we have a set of apps that, don't have the location permission, and then we have a set of apps that are transmitting location data. One would reasonably expect these to be disjoint sets, but in fact, in our research, we found that this wasn't the case. We specifically found over 1,000 apps that were transmitting fine-grained location data without the permission to actually access it. And we found several different explanations for this, but one was, lots of side channels that were actively being exploited by various SDKs. So on Unix, the proc file system has, it's a virtual file system that has, various information about the state of the device, and that includes networking information. One of the virtual files in there is the ARP table, which lists the hardware address of the upstream router. In the case of Wi-Fi, that's the MAC address of the connected Wi-Fi router. And that, we know is a reasonable surrogate for location data because Wi-Fi routers tend to be in fixed locations, which is why normally there are multiple permissions that are required to access the information about the Wi-Fi router's MAC address. But instead, an app can just read it from the ARP table in the proc file system, thereby circumventing those permissions. And so here it is in action. Here's the assembly from a particular SDK, and it's checking to see whether the app has the access Wi-Fi state permission. If the answer is no, it jumps to this function called get device MAC address from ARP, and it just reads the procnet ARP file, thereby skipping the need for the permission. And we found that this is pretty pervasive. So we found a lot of different SDKs that use this same technique, and we find these in hundreds of apps with potentially billions of users. And it's likely that in many cases, these are popular SDKs. It's likely that the developers have no idea that these SDKs are collecting this information, which could create potential liabilities for them if they're putting disclosures about the fact that their app doesn't collect this data in their privacy policy, for instance. And so, the point that the point of this whole talk is that many of these bad behaviors seem to come from the SDKs. And so what does this actually mean for compliance? Well, due to third-party SDKs, you might not accurately be disclosing your app's privacy behaviors, and therefore your app might be collecting data without required consent. Maybe you're in a region that requires consent for certain data collection activities, and if you don't know that the SDK is collecting this data, you might not be correctly getting consent, and therefore might be at risk. And so, this is all to say your app might be violating laws without your knowledge. And so, the final takeaway is what do you do about all of this? Well, I mean, for developers as well as organizations that are releasing software, read the SDK documentation thoroughly when incorporating third-party SDKs with an eye towards behaviors that might have privacy ramifications. Oftentimes developers have a lot on their plate, and so they just want to know what functions are relevant to get the job done. But that's obviously creating, potential privacy issues when you're not looking at options that could have a bearing on privacy. More importantly, you should make the compliance people in your organization aware of all of the third-party code that you're using so that they can also look into this stuff to double check and make sure that the disclosures that they might be responsible for are actually accurate. And then finally, this is all to say, test. We find this stuff by testing lots of apps, and I'm of the opinion that really that's the only way of figuring this stuff out, because oftentimes, the documentation might be hard to understand, or it might be, an SDK that's just not disclosing what it's actually doing. And the only way you're going to find that is by actually just running it and looking at what the app is actually doing, both through, debug logs as well as what's going out over the network to make sure that all the data that's being sent is accurately disclosed in your privacy policy and is in compliance with relevant laws. And with that, I'll leave it there. Thank you.